Yeah. So good morning. I'm going to be talking about a few things. So I'm going to be doing Kepler, TESS, and Gaia. Okay. So again, like we've mentioned, I'll be showing you Jupyter notebooks. Obviously, this would be like a starter. There are lots of details. You can have the whole meeting on TESS, but this is with that. Okay. So we'll start off with. Yeah. Okay. So a lot of young students are interested in exoplanets and strange new worlds. Actually, the number should be updated. Now it's already crossed 5,000. Okay, this is an earlier number, but the number of known exoplanets has very strongly increased. And that's basically because of Kepler and TESS, right? Now, the simple principle which is used in Kepler and TESS, both of them basically work on the transit method. Okay. If you remember Michel Meriot and Didier Collet, they got their Nobel. That was basically done using the radial velocity method. But in Kepler and TESS, you have radial velocity data as well as transit data. Both of them are there. I'll show that to you. And basically, the principle is that if a planet transits in front of a star, you're going to get a fall in the light, and that's what you're using as a signature, right? And the basic, this is sorry, this is what is called the light curve. And this basic light curve is, actually, I'm going to show you how using Kepler data, TESS data, you can get a lot of the parameters for your exoplanet. And then we'll take it ahead to Gaia, where Gaia you're getting parameters for the star. So then you can get parameters of the host star using Gaia data, right? So for the host star, you'll get your, you'll get your distance, you'll get the proper motions, etc., using Gaia data. Okay. But first we'll start off with Kepler. So for example, we'll be using this. That's very simple thing is that in your light curve, you basically can use the depth of your light curve. Your depth is basically a ratio of the squares, right? Area squares of the planet and the star. So therefore, you'll actually see that the ratio of that, if you know the radius of the star, you can actually find out the radius of the planet just by measuring the depth of the light curve. But what you can see, I want you to notice this one. This is a Kepler light curve of an exoplanet. And what you can see, please look at the y-axis. The y-axis is the relative brightness, right? So you can see that the relative brightness, you can see it's from 1 to 0.994, right? Those are the transits which you can see, these dips, right? These dips are the transits. And you can see that the value over here is like 0.994, right? So the biggest problem in these transit observations is that the accuracy, it's like it's a 1% dip or even lesser than that. And that's why you actually need to go out to space, right? So Kepler TESS, both are space telescopes, basically because using ground-based telescopes, you may get a fluctuation which may be because of another effect, right? The atmosphere, it could be anything else. And it would be very difficult to detect it. And therefore, it becomes very important to send the telescope out into space because this is the kind of accuracy you're looking at, right? That's the problem. And like you have for any signal, we generally say you need a 3 sigma threshold. That means your signal should be 3 times more than the noise. Typically for transitory exoplanets, if you have an exoplanet like this, where you can clearly see 3 transits, right? Then that is taken as an indicator of the exoplanet. If you have a single dip, it will not qualify. You should have 3, right? That's the standard, this thing, right? That you should have 3 transits to confirm it. But based on the transit observations, you can actually get the size of the planet. Like I showed you, it's the ratio of the radii of the star and the planet. You can also get the number of planets. This is a very simple transit you can see, but there's a single dip. But in reality, life is not so simple. And what happens is that if you have a multiple system, then, and obviously all the planets will have different orbital periods, right? So obviously your light curves are not going to be so neat and nice. You're going to have extra dips coming in at different points, depending upon the, depending on their orbital periods, etc. They all won't overlap like this. But so the other important thing which you can immediately get from this is, the orbital period right? Because that is what you're seeing in this. And directly using that, you can find out with Kepler's laws, you can find out the orbital radius, right? So we are actually going to see how do you find out all these parameters using the light curve. So first I'll explain to you how do we do it, and then we'll actually see it through Jupyter notebooks. How do we go about getting the light curve, right? So that's your thing. So now the thing is that in case of binary stars also, that's another big problem. Actually, it's not exactly a problem. A lot of the binary star community uses Kepler data or TESS data because essentially, again, you're getting transits. So typically, like what you can see on the top is if you have a binary star, right? Both those, it's quite similar to the kind of kind of light curves you will get with the terms of exoplanets, etc. So a lot of the binary star community actually uses Kepler and TESS data because it's the same data, right? Which it's a part of the sky. Okay, I'll come to that in a bit. So like I said, using this, I'll show you with Kepler. You can do it with TESS also. You'll find out the orbital distance, that is using the period. You can find out the radius of the planet with the dip. You can find out the mass of the planet, and then I'll even show you how can you find out the temperature and the chemical composition. So first of all, let's try accessing data. That's the first step. Let's first do that. So like I showed you on the first day, the astronomy data archives, all these are sitting at the MUST or the MAST, which is the Space Telescope Science data. And this is what is called the HLSP, high level products. So you can access, from this you can access Hubble data, James Webb data, Kepler. There was a problem with Kepler, so then it was slightly modified and it was renamed as the K2, that is the second phase of Kepler. So Kepler, K2 as well as TESS. And you can access all this using this data. So first I'll show you that in a way which could be simple. Okay, this is showing this. 1 minute, huh? I will make it, I should have made it to my whole desktop. Okay, so I'll do the whole desktop. Yeah. So the simplest way, I'll also show you how can you query it through your Jupyter notebook. But otherwise, what you can do is very simple. You just say MAST and you say Kepler LHSP, right? That is the high level products. So once you give this, you'll immediately come to this, which is the high level science products, high level science products for Kepler. Oh God. Okay, we'll come down here. Yeah, this is fine.
Ma'am, we cannot hear
Oh
you.
God. When I did the stop share. Okay. So I'll just repeat a little bit. This is the website we go to if you want to download Kepler data, right? Like I told you, I will also show you how do you download this data using the Jupyter notebook, right? What's done is generally there are more than one ways of doing the same thing. So you just choose whatever suits you. So what happens is for a particular target, here you have Kepler targets put over here. These are the first 5 targets, for example. You can download any one, whichever you like. And one is the time series data. And you can see that the other thing what they did is you also have the radial velocity data. So this one is this, and you have the RVB, which is that, right? Now, since we do not have too much of time, trust me, you can do it on your own. But here I'm opening something which we did not get the time to talk about. But some of you all who've been here earlier, there's something called TopCat, right? Basically, TopCat just opens tabular data. Okay. So from here itself, you can download this data, right? You can download any of this, Kepler 6b or whatever. If you want, you can click on the target over here, and then this will show you the target. This is actually giving you the details. So if you do the analysis, if you're trying to learn analysis, you can first take it from here, see what are the parameters, etc., and then see how does it work out when you do it yourself, right? So if you download this thing, the text file, this one is, like I told you, the time series one. This one is the radial velocity, which has this extension RV, right? So RV is the radial velocity file, while this one is the basic thing. So if you actually download that one, which I've already done it over here, and you see the plot, this will look something like this. Right, 1 minute. I'll just, yeah. This is going to look something like this, right? It looks something like this. Now you can see clearly there's a periodicity. You can see there is a periodicity, but obviously what happens is the observations are at different points of time, right? So you may catch the transit at different points with different sets of observations. And therefore, what we do is, yeah. So here you can see, there's on top, there's this thing. On top cat over here itself, there's file and load table, right? So don't worry too much about the TopCat part because we'll be doing it with a Jupyter notebook, but I'm using the TopCat thing basically to explain things. Sorry. Yeah. So this is our plot, right, which I just showed you in TopCat, which obviously looks this thing. And therefore, a standard thing which is done is what is called folding, okay? Because our observations are at different points of time, right? And so, for example, I'm catching this thing at different points. And therefore, if I want to improve my light curve, what you have to do is fold, right? Now, folding means the simple function which is used for folder is the modular function. I hope you all know what is modular, right? So what is, for example, 9 modular 4? What is 9 modular 4? 1, thank you. Yeah. So you're basically dividing and taking the residual, right? So essentially what we are going to do in here is you have this y, which is the observation time, and this is the period, okay, which is obviously observable from your plot itself. You can look over here and these are Julian dates, okay? This on the x-axis, these are Julian dates. And basically what you're going to do is to fold the function, when you're using modular function, you have to estimate the time period, and based on that you can fold it on TopCat for this particular exoplanet. Why is this? For this particular exoplanet, the time period is 3.2346. Okay, so I will show this to you in TopCat and then I'll show it to you in Jupyter Notebook also. So what happens is you have to basically fold the function, because like I told you, all these points are at different, at different parts of the epoch of the transit. So therefore, you add all these together, and with this is a folded light curve. So for example, you may have an observation of, I don't know, 50 transits, depending on whatever is the observation time. And then when you fold it, you get this nice light curve, which is something good with which you can analyze. And like I told you, the light curve is where all the analysis lies. For example, number 1 is the period. Number 2, you will see structure in that, supposing there is multiple systems, right? Or various other things. And therefore, the light curve folding is something very important so that you can actually get a good set. We'll do this. I'll show it to you. So here you have the light curve folded. Once I have the folded light curve, right? Then the simplest, like I told you. So if I'll show it to you in the analysis that if you put the wrong period, your folding won't happen well. You will get breaks, etc. And therefore, what happens is you have to get your p value very well. But once you get your p value very well, all of you all know Kepler's third law. So you already have your p squared, which is proportional to a cube. You put in the values and you can perfectly calculate. You can see over here on the right hand side, we don't know the m star. We'll later on figure out how to get the m star. But other than m star, all the things on the right hand side, these are all known quantities, right? So I know the time period, I know all these things, and I can find out the distance of the planet from the star, right? Okay. Now this is also something I'm going to show it to you, that to find the m star value, there is something very important called the Extrasolar Planets Encyclopedia. And I'll show you that website. It's exoplanet.eu. And from there, you can actually select your exoplanet system and get the mass values, right? That you can get from there. You can also calculate it even using Gaia or using some other methods. Also, you can do it. But to start off with, this is good enough so that you can put it in your formula. For example, if you put it into this formula, you can calculate the orbital period, right? Once you get the orbital period, so I will show you from that website where you can actually use it to get all the parameters for the star. For example, you can get the mass of the star, the age, the effective temperature, the radius. These are very important things because you all know that for exoplanets, we are interested in habitable zones, for example, right? So you need to know the temperature of the star and you need to know the distance of the star so that you can actually check what is the kind of temperature that is present in this thing. Now, habitability is defined as the distance at which water is in a liquid form, right? So you basically need to know the temperature and that will tell you whether water is in a liquid form or no, right? So that we'll get from the star date. So once we have this, you can actually, from this database, you will actually even get the radius of the star. You can see the radius is here, 1.39 Arson. So you have the radius of the star. And once you have the radius of the star, you can actually measure the size of the planet. Okay. And how do you find the size of the planet? You're basically getting the amount of the dip, right? Because the dip is what? The ratio of the areas, right? Rp squared divided by R star squared, right? So you can even put it for the Earth, for example, and you see what you're going to get is, very small number. So that is, it obviously depends on the precision with which you have your light curve. So you have to take the F total minus the one during the transit, and the F total, this is the ratio of the areas, which is this. I already know R star because from that extrasolar database, I get that. And I get that. And hence I can find out the size of the planet. Now I know the size of the planet and I know the temperature of the planet. So I can get the, I can get the temperature of the planet, which is given to me by this. The temperature of the star, I'll get it from that extrasolar planet thing. I know the value of this, and you have to actually put in a value for alpha, which you can, which is another headache. Okay. The other important thing is if you have the radial velocity data, then you are basically, that's the case in which you can actually calculate the mass of the planet. So radial velocity data is very essential to get the mass. Otherwise, you will not get the mass of the planet. So therefore, you'll see with Kepler data, TESS data, there's always supplementary data which has radial velocity because that will give you the mass. And once you know the mass, then the way we proceed is you can get the density, right? Because we found out the mass, we found out the radius. Using that, we find out the density. And the density is very important because that will give us the composition, right? Because you're there, you know the planet composition. So these are some standard plots where you can see the mass versus radius. Here you can see Jupiter, Saturn, Uranus, Neptune, Earth, Mars, whatever. These are all plotted on this. So once you calculate the, the density, you can approximate the composition of the planet, right? Which will then answer more stories about what would be this thing. So for example, this planet specifically turns out to be a hot Jupiter, right? And we'll this thing. So there's an assignment. I will be sharing this PDF with you all. So you'll see an assignment where you repeat the procedure for more, but I will first show it to you in TopCat. What are we doing? And then we'll do it in Jupyter Notebook also. So first we'll do it in TopCat. So as I showed you in TopCat, this was the thing we had. What was the what was the period? I keep forgetting that value. 1 minute. I'll just open the period value was 2.2346, I think. No, because I need to know that to do the folding. 3.2346. Okay. So this is my data. I have an extra column over here, which is already I've calculated. So one column, this is the Julian dates. Sorry, I'll zoom it. It doesn't want to zoom. Why is it not doing it? Okay, anyway, so this first column we have are the Julian dates. Here, this column is the phase, right? This I've already calculated. So how do we calculate it? This is in TopCat. Don't worry about how to do it because then you are going to be basically doing it with your Jupyter Notebook. So what we actually do in TopCat is I can call this phase. and I have the modular function, which is this call 1 and 3.2346, right? Right. So this is the phase. Okay. So now when I plot versus the phase, that's when I get the, sorry, I should have done the other thing. I'll do phase versus call 2, right? So this is when you can actually get this folded function, which I was talking about, which is the important thing, right? Right? This is the folded function I was showing you. Now you can actually see, I'll show you that, for example, if I were to put a wrong, this thing. So let me put a wrong modulus. Supposing I put modulus, it was what, 3.2346, I think. So let me put 3.4, for example, right? 3.4, but I put, oops, all one with that. You'll see that if, you'll see you're getting a total mess, right? If I put the wrong period. So if you put the wrong period when you're folding, you'll get something like this, right? Now, there are many ways of figuring out how to fold it, right? One is you just do trial and error, but then there are sophisticated programs also which you can actually use to figure out how to optimize, right? Which we've spoken about, how to optimize the value so that you get. So if you do the wrong one, you'll get something like this. If you do the right one, then you will get something neat like this, right? And this is all you need. Once you have this thing, then you can find out all the parameters for the exoplanet, right? Okay. So I just did this to show this to you, but now we will go on to our Jupyter notebooks, right? So what you have to do is I've already put them on my GitHub page. So here's the GitHub page. And okay, first I'll open the, this is the, which one is the one? This is the Kepler one. So on that GitHub page itself, you'll find the Jupyter notebook for Kepler 5b. Okay. And all the code is there. So if you want, you all can open it. Huh? You know, right? How you very simple. No. So you'll just say GitHub. Say GitHub. Sorry, 1 minute. It didn't do this. You say GitHub, right? I think one of you all only told me this was the simplest way to do it. So get onto GitHub, right? And then you can do Hasan 13, right? You will come here. Yeah. And come on. Why is it not doing that? Okay. Yeah. So first open the Kepler one, then open the TESS one. First we'll do the Kepler one. Yeah. So look down. TESS. Okay. Kepler is not there. Okay. Doesn't matter. Then we look at the TESS one. Okay. The Kepler one is very similar. Very similar. Let's open the TESS one. Okay. So you can open the TESS one. I'm already opened it, so I'll just reopen it here. This I opened this from Kepler 5b. How come it's not here? It's there. You didn't find the Kepler one. What's the name of the file? Okay. This is Kepler 5b. See, this is in, it's there in Hasan. Isn't it there? It's there. See, it's showing that it is there in Hasan 13. This one is the Kepler 5b. The Kepler is not there, nahin, for some reason. Okay, doesn't matter. We'll open the. Okay, let's open the TESS one then. We'll open the TESS one. Okay, yeah. I didn't update it. So, I just update it like this, or how do you update it? No, but it's not this thing. So yeah, that push and pull business is there, no? What do you do? Okay. Anyway, let's just go to the TESS one, no? That will be simpler. It's the same thing because the data is very similar. No, I didn't update it. That's what he's saying. Yeah. So open the test one, open the test file. And basically what we are going to do is I will show you how to access the data. Once you access the data, then you need to fold it and get the thing, right? Now, before that, I should show you, I'm sorry, but I'm just going to show you something very simple about TESS and this thing. See, these are these two satellites, right? This is Kepler and this is TESS. This is Kepler, this is TESS, right? And what they have is they're slightly different in their this thing. Kepler just looked at one part of the sky, okay, a very small part of the sky, and it was a 12 by 12 degree patch of sky which it observed. That is all it. TESS, what it did is basically it covered the almost the whole sky, right? So if you want to check for exoplanets almost in any part, there are few holes, right? But on the whole, it's the whole sky. There are basically so they basically like it's written over here, they differ in their observation strategy, right? So while Kepler observed only one patch of the sky, TESS, it actually divides the star into sectors, okay, and it spends a month looking at each sector, and then what it does, it keep repeats it, so it in that way you get your data in terms of these sectors and things like that, right? The idea of this being is the James Webb, that is what is called an observatory class telescope, okay? So what it will do basically is that you have candidates which you get from Kepler and TESS, right? Kepler, like I said, it's only one part of the sky. TESS is mostly the whole sky. What people are expected, or what they do with that, is that you use that data to actually get candidates, good candidates. The James Webb cannot be used to search for candidates, okay, because it is an observatory class telescope. It will only do targeted observations. So the idea is, therefore, if you work on TESS data or Kepler data, it plays a very important role, because with that you can identify your candidates, okay, which will be used by James Webb, right? So James Webb only uses confirmed candidates. So you have done all your Kepler TESS analysis, right? Based on that, you find out all these basic parameters for these planets, right? You check on their habitability, on their chem composition, on various things, right? And then James Webb will give it a deeper, better look, because you basically check whether, with what accuracy will you be able to do spectroscopy. Basically, that's what James Webb will do. It will check out the atmospheres. But for that, you need to have your candidates, right? And therefore, there's a lot of, and then, like I said, specifically with TESS, you almost have the whole sky, right? So then there is obviously the astronomer community is not sufficient to actually set, so there are even citizen science projects which are exoplanet hunters, planet hunters, where people can actually view the TESS data and Kepler data to actually look for transits, because it is you can have other things that can cause transits. So people need to shortlist. So therefore, it's a very valuable thing if you actually do this kind of work, because this could feed into your James Webb proposal. If you want to give a James Webb proposal, it will obviously mean that you should have analyzed all this data, and that will be part of your proposal to justify why you want to observe a certain object. Okay, so like I told you, so we are going to now this thing about the TESS, this thing. So what you can see is that in many of these missions, you have automated pipelines. So the one for TESS is called the Science Processing and Operations Center, SPOC. And basically what SPOC does is it will basically, your data release products, which are given to the community, is raw full frame images, there's calibrated images. There are what are called target pixels, light curves, flat fields, etc. All these things. So what happens is, like I told you, the TESS sectors, they cover about 24 degree by 90 degree strips of the sky. And then what it does, so these ones have a cadence of 30 minutes. Cadence means when you take your observations, okay? And then there are also, TESS works also on what is called objects of interest, TOIs. So then if there are objects which are identified, then TESS will revisit them for the different cadence, right? In astronomy for transits, a very important factor is cadence, because it basically means how do you space your observations, right? So if you space it too widely, you may miss out. And if you space it too closely, it's too much of time. So you're not going to get that much of time for observation. So there's a play between the two. So what happens is there's a package in TESS called light curve. The same package can be used for Kepler data. What I showed you all with TopCat. TopCat is just the thing to understand it, how to do it, but you can actually use the code from here. So you can use this light curve to work with this. And what you need to do first thing, you all can try doing it in your Google Colab, is you obviously install light curve. Okay. Like I said, you can use it not only for TESS and Kepler, you can in principle use it for any light curve. There is no such thing. Obviously, this is a little fine-tuned for these, but you can use it for whatever. So you'll pip install light curve. Okay. Once you do this, our usual Python style, you will import it as LK, import NumPy, import Matplotlib. These are your imports. These are your imports. Now what happens is, the data products in TESS, one is what are called full frame images, which is a sector image. Okay, but the sector is a very large area, right? Your object would be what is called a postage stamp. So what happens is, so the full frame images are FFIs, the target pixel files are TPFs. These are postage stamp cutouts of the stuff you want. These have generally a cadence of 2 minutes or 20 seconds, depending. And then there are light curve files, which are the ones. Like I told you, TESS has both modes. One is the survey mode, one is the TOI. So we are going to see that now, for example, if I want to get TESS data products from the MAST, one is what I showed you, that, MAST, we wrote Kepler HLSP. Similarly, you can do TESS, high-level science products. That is, you can use it through that, or you can use it from here. So basically, but you're accessing this site. You are accessing this site, and you are actually this thing. Once you do that, I will see how you can actually get the data, and you give your object, you get the light curve. So you observe your light curve, look for the target pixel files. We are going to look for that and then obtain the light curves. So first of all, we are doing this step. We've chosen a certain exoplanet, L9859, which is a planet around an M-dwarf star. I hope you're aware that most of the exoplanets are around M-dwarf. That's the typical kind of star where you're going to get them. So we are searching. We'll search for the large sector. This is the pixel file, and this is the light curve. So we are actually searching for the data that's there in this. Like I tell you, you need to search it because it could be in TOI. It will be the normal one also. So in this case, this is also a TOI. So we'll get both. So we'll search. I mean, I hope you all are running it. You can run it, right? If it's there, because, yeah. Now what we are doing is, now we are setting the sectors. What is the data in the sector? So you can see that this object, it has 21 data products. This is the target which we wanted, and it's telling you the different exposure times for we had it. So this was one of those shortlisted exoplanets. So there is a target of interest also. You have all these observations. So in this, what you can see is, obviously you can see the sector that's there, which is the sector, which is the year, which is there. So for survey data, it is TESS data, but if it's a TOI, then you may have a PI, right? So there's somebody who owns the data. The cadence of the this thing, all that is there over here. Now here I'm looking for the, like I told you, we are looking for a target pixel file if it is a TOI. And I have already told you the suspense that it is a TOI. And therefore you can see that here SPOC. SPOC is the TESS processing thing, but you can see that there are some data sets which are by other people also, and you'll see these are there. So these are the target ones. Now the light curves, which are the light curves available? Here you'll get the names of these guys who observed it or whatever, which groups took it. So you have different names in these authors, right? So you have these ones. Now here is your light curve. So now you can refine the light curve, because what we want is the light curve. So you will say the search light curve redefined. This is the one. This is the object. We are taking the SPOC. We are taking the normal TESS one. Exposure time 120 seconds. And it's a 2-minute cadence, which they have for that.
So here we are taking observations which are observed after 2 minutes.
At to 2 minutes spacing. Yeah, spacing. The important factor I told you is that cadence, the spacing, because that will affect What happens is because of this, there are, we don't have the time to talk about it, but there are certain classes of exoplanets which are more observed, which have a cadence of a few minutes. But if there are ones which are with different cadence, then you may miss it out. So that's part of the deal. Okay. So what you have is then we have this thing. And so now you see in this, so we'll download the stuff that's there. Sorry, this is taking some time. And so actually what I showed you all on the first day, Vera Rubin Observatory, that's again basically looking for transits. But the problem is you have the whole sky, so how often can you revisit, right? That's the problem. So here we have our LCFs. This is your light curve collection. And here you can see this is the first data set which we have, where you actually have the time period. See, this is very similar to what we saw in that other file. This is the timestamp, okay? Here is the flux, right? And then it's exactly like we did it in that TopCat file. You have your time, you have this thing. This has many more other parameters. Don't worry too much about them. You basically want to know the time as a function of flux. How did the flux change? That's what you basically need to know. And so in some cases, like in this table which you see, which we have over here, you're given the time and flux. And there are still more these other functions, sap flux, whatever. These are part of the processing thing of measuring the photometry. So this sap is simple aperture photometry, and there's this other kind of photometry which you can do. Now what we do is we can plot the curves, and this is the kind of curve you will get, right? If you actually look at this curve. Obviously, this black part is messy, and there's there are different tutorials available. You'll get the link in this, that you actually need to clean it. So for example, this light curve, first thing you need to do is what is called flattening. That is, you remove long-term trends, okay? You have to remove outliers. You may remove values which are infinite or nan values, because see, another important thing with all these satellite data is that since the data volume is so huge, they just go through pipelines, right? There is no individual who's checking the data. So that's the biggest challenge with these, that because it goes through pipelines, it gives you what it got, right? So you may get infinite, you may get this, you may that. You have to, clean it out, because there has been no human touch to it. You are the one who's first time giving it that human touch. And then the next thing which we do is the folding, which I showed you. You may also want to bin data. I will show you in this example how binning data is also very, very important, right? So here you will have, so here is the data. This obviously doesn't look at all like what I showed you, the data with that other Kepler, this thing. So what we know, we need to flatten it. We are there, and all these things are luckily tasks which are available in it, with which you can kind of this thing. And now comes the important step of folding. Obviously, the important thing in this is what is the precision with which you know the period, right? So here you can actually find it out from somewhere. So you have the folded light curve. This is the period, and you get this, but still you don't see something very this thing. So therefore, what we do is we do binning, okay? All these things here, we are actually giving you the values, but you will see that when you're actually dealing with real data, for each object, it's going to be different. And therefore, when you bin it, you're going to actually see different. But now, after we fold it and binned it, here you can actually see your transit, right? Which is what we want. Once we have this transit plot, right, then I already showed you in the beginning that from the transit plot, remaining all parameters you can find out, right? You will know this period. Here we know it to this precision, right? The period is 3.690621. So with this, I can find out the orbital radius. I can find out the star parameter. I'll show you from that website, and you'll get this light curve. And once you get the light curve, you basically have to plug it into your different formulae, and you can do various things. Now, I'm not going to do this thing of interacting with your light curve, but there are many, it's there in the notebook. You can try it out. There are many things which you can do further with these things. Exoplanet people, it's an art of how do you handle the light curve and get various things. But basically what I showed you is how do you get it to this stage. This stage is the stage from which you can calculate all the other parameters for it, right? Uh, I'll just show you this thing, this other website, which is a very important, website. Europlanet.eu. This is the one from which we got all the stellar data. Okay, the data for the star. Come on, come on. Oh, no, 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 not GR. Where did the GR come from? You'll find actually you'll find the website from this presentation itself, which I'll share. No, where is the value given over here? Yeah, exoplanet.eu. I wrote the wrong value, wrong thing. So there's exoplanet.eu. Okay, and here if you go to catalogs, right? So since I've already done it, it's already fed in here. There's a little cryptic way in which you got to feed in the data. You have to write it like this: Kepler 6b in name. This is the name column. If you filter it, you'll see it. This will give you, this is going to give you the data for your object. So this is my Kepler 6b. And if you click over here, this is giving me all the details about the planet and all the details about the star, right? So if you pick up any data set from, you can always confirm, check the values which you get using this thing, right? Now it really breaks my heart that I'm at 10:29 and now I need to tell you all about Gaia, which is what I've been doing for quite some time, but there's little time. So in short, that's how you'd basically analyze your Kepler test data using those kind of notebooks. They are available on that GitHub thing, right? I'll just update the GitHub thing. So you'll be able to access it and run it. Using that, you can actually get all the parameters. A lot of students who were participating in our things earlier and all that, a very simple student project one can do is just of analyzing exoplanet data, right? So you take it, check out some exoplanets from that website, you can check it out and you can actually analyze it, see the values you are getting. Maybe you will be able to get the period to a higher precision, right? Maybe in the website, you'll see it's there till say the third decimal place. Maybe you're going into higher precision using some other method or something like that. But that can work out very well. I have even done it for school students because using TopCat, even school students can do it. And a lot of school students also have done projects like that because it's reasonably easy and interesting. Okay. Now we'll focus on what about the stars, right? So this one is one, okay, this is the HR one. Okay, I'll show you this one. Okay, this is also there on that GitHub page, which is with Gaia data. Now, all of us know, I mean, hopefully we know that stars basically form in groups, right? And you have what are called open star clusters and globular clusters. Open star clusters are the younger population, which are in the disk of the galaxy, while globulars are in the halo of the galaxy, made up of older stars. We don't have too much of time, but there are basic differences between these things. Now, what is Gaia? Gaia is basically a European Space Agency satellite. And what it basically does is amazing. It, since the time it's been launched, I think I've been just working basically on Gaia data. What it basically does is it observes about 1 billion stars in our galaxy, right? For which it very accurately measures its positions and its velocities, okay? And once you measure the position very accurately, you can measure the parallax, the shift in position, which will give you the distance, right? Now that is very important for studies of star clusters for the simple reason. So in short, Gaia gives you astrometry, photometry, spectroscopy for these stars. What it basically gives you, so the Gaia data obviously gives you the right ascension, this thing, it gives you parallax, which gives you the distance. It gives you radial velocity and proper motions. And it's very, very important because if you have star clusters, think of you're a group of people over here, and I want to figure out which group has come from the same place, right? All of you all have come from different places. If I want to figure out which group has come from the same place, I look for parameters, right? And I look for the parameters which match, which are close. And therefore, what happens is with Gaia data, you know the distances, you know the velocities. So if stars were born together, they are at the same distance, they are moving with the same velocities. So therefore, if you can pick up stars which are with same velocities and this thing, then you can actually identify members of the star cluster, right? And that is very important if you want to, for example, find out parameters for the star cluster. For example, what are the masses of the stars? What are different parameters of the stars? You can only find it out if you know which are the members, right? Otherwise, if I take the whole sample over here, there are many people who do not belong to the sample. So my whole sample will be messed. So if I want a clean sample, I need to do it with that, right? Now that can be done. What I'll show you today is something very simply how it can be done. What my student Mudassir is going to show you is we actually applied machine learning to Gaia data because the number of stars are very large. And therefore, you can actually apply machine learning to get a better sample or a larger sample of member stars. So he's very soon going to submit his thesis, and his basic thesis is machine learning using different techniques with Gaia data to actually study star clusters and then get their parameters and various features. So this one we are going to do is a simple one, but so in this very, what do you say, in this very notebook, you will see, yeah. So in this very notebook, you will see that, for example, with a Jupyter notebook, I can go to a website, right? So what we are going to do is we are going to go to the Gaia archive itself. In principle, you can go to the archive through your browser also. You can go to it even through Topcat. But here we are going through the notebook. So if you go through the notebook, you can actually press what is search. You are now on this thing. I can give my object. For example, if I give M4, for example, Simbad resolves it, right? I can say what is the radius in which I want to look for my stars, 5 arc seconds or whatever, 15 arc minutes, whatever I want. This is looking, there are various data sets. The Gaia had various data releases, data release 1, 2, 3, 4. Sorry, 1, 2, 3. And this is the latest release. And you can submit your query, right? So in this way, you can actually get your data from here. These are the usual imports. So I'll just run this fast. You can also, another way of querying it is, one way is through that. You can also query it using AstroQuery, which is a part of AstroPy. So if you use, you'll have to pip install AstroQuery. This is there on that thing. So we'll import this stuff. And this is the standard syntax with which you need to query it. So for example, you'll say, for example, the coordinates are this. These are the coordinates for M45, for example. I've got the coordinates. This was shown to you by Sir the other day. How do you get the coordinates from the name? So you have the coordinates. I took a radius. This is in degrees. So this is degrees divided by 3. So 20 arc minutes. And I am here querying. Query is J is querying the thing with the coordinates radius from this table name. You want it bigger? 1 minute. Oh God. Okay, this is nice, no? Yeah. So now here you have this code, so you need to basically follow the syntax. Huh?
Sorry, these notebook we are accessing.
Yeah. Why are they blank? Okay, I'll just check on that. It's because. Uh-huh. Actually, even I was a little confused. You can open it from GitHub. Some of my notebooks were opening in Collab from GitHub, but some of them were refusing to do that. So I had to, from Collab, open the GitHub. Ideally, both should work, right? In this. The other option is you download it and upload it in your Collab.
I have downloaded and running in Jupyter Notebook.
Huh.
And also these lines are coming back from
Okay.
AstroQuery, almost till the HR diagram.
Okay. Okay, I'll just check on that. The problem is I'm already dipping into Sushan's time, so I will try to just rush through this. I'll check on that. That's just some technical thing. I'll just check it. But essentially, you have to follow this syntax. So if you have the notebook, you can put it and run it. Right?
It just says missing attachment. It says 2008
Okay.
lines. It can see, but it's not open.
Okay, I'll check.
It is there.
Okay, I'll check. I'll check. Yours is opening fine. Okay, I'll do that. I'll just do that. I'm saying dipping into Sushan's time, so I want to finish a little fast. So this is an astro table format. You'll have already seen what is astro table format. So that is the R, which is the data set. You can see here is the data set, which is basically the data for M45, right? So you have your object and you have various parameters. Now, what we are going to do is you can read it, whatever, you can do various things with it. Now, what I prefer to do generally is I convert it to pandas, because if you do it with pandas, then you can do various other things. And then, for example, if I want to plot it, here is a sky plot of M45, but obviously I do not know which are the members. So what do I do is, you can see this is what is called the HR diagram. We don't have time to talk about it, but this is a diagnostic diagram of stars. I think I should reduce this a little bit. Oops. Yeah, so this is what is called an HR diagram, and this is what is called a messy HR diagram, in the sense these stars obviously do not belong to the cluster, right? Earlier, in good old times, when I did my PhD, we used to clean the HR diagram just by making a filter over here with a certain width and throw everything else that was outside. That's what we just did. But now with Gaia data, you can actually do that in a more organized way. So what we actually do is, like, for example, here you can see this is a plot of the proper motions in DEC and in RA, right? Now you may think that this is the cluster, but this is not. This is not the cluster, because you can see this is centered somewhere around 0, 0. These are all a set of foreground stars and background stars, which are so many. While the cluster stars are these ones, these poor ones over here. Okay, these are the cluster stars. This is the mess. So you can see this is the problem which we have, that you are actually wanting to pick up so many stars from this kind of a sample, right? So most of the stuff that you have is a mess. You don't want that. You want only these. So what we do is we actually make cutoffs. You say, okay, I am going to take all stars which lie within this range of proper motion and this range of DEC, and I do that. So similarly, if I plot it versus parallax, parallax is such that 1 upon parallax is distance. You can see again, you get a lump. This one is the cluster lump. So what we did in a very simple, this is with proper motion DEC. So what you can do is, if I make a histogram plot, you can see that this is the lump which is near 0, which is the field stars. These are the cluster stars, which are around this point. I can even do it with PMRA, PMDEC. That's just done just to look at this thing. I can describe the data, I can do it. And now this is the important thing, which I make a mask, okay? So using the data, I inspect the data to make a mask and decide which ones are members. So where did the mask go? So you can see there's a mask where I say all stars which have a parallax. This is something between 7 point something. So all stars with parallax between 6 and 8.5, PMRA between 10 and 30, PMDEC between that. You use that as diagnostics to inspect it, and you apply the mask, right? And once you apply the mask, those are your members, right? Like I told you, this is a rough way of doing it. You can do it in a far more specialized way. But when you even do it in a rough way like this, you can very well get out your members. And therefore, the end product is what I'll show you over here. And this is what we called a clean HR diagram. So what you can see is the orange stars are now the members, right? This is a clean HR, while the blue ones are the mess. And these are wrongly identified, right? So you have to then apply some more techniques to further filter it and this thing it, right? And here is my clean HR diagram, okay, which you can use for this thing. So I'm sorry, I'll end with this because I need to give it to Sushan. But the notebooks are all there in GitHub. I'll just this thing it and you can run it, and I hope that will do well. Fine. So I'll stop. Any questions or what they're all clear? Yeah. Yeah, so Gaia, now the data really, you have the girl sitting behind you is working on time series data with Gaia. So the earlier releases did not have it, but yes, as the data release as this thing, yes, now you can. Yes. And as the next ones come, you'll get even more better time series data. Yeah. Yeah, yeah. And it's all sky. Gaia is all sky. So finally, by the time the mission is completed, it would have visited every star 70 times, approximately. So that's a lot. Yeah, that.
Is there a DR4 plan?
Yeah. DR5 is also planned. But just now, they've not yet given out the dates for DR4. DR3 was last year, June. It was a birthday present for me. That's why I know the date. But they've not yet given the dates for DR4. But yeah, there's 4 and 5 is there. Yeah. Okay, come, Sushan. Thank you. Nahi, 1 minute. Now I'm so confused.